Hello, in this video, we'll talk about predictive and preventive mechanical maintenance. Before we continue, remember to subscribe in our channel, like the video, and active the notifications. It helps us to grow in YouTube. Maintaining machinery and equipment is essential for a company to stay efficient and competitive. When maintenance is overlooked or done improperly, it can result in costly downtime and production delays. Predictive and preventive maintenance are two approaches that can greatly enhance machine availability and operational efficiency. By staying on top of these practices, a company can ensure its equipment runs smoothly, helping to meet deadlines and keep clients satisfied. Industrial operations often struggle to keep machines and equipment in top condition. To tackle this challenge, it's essential to regularly monitor the performance and functionality of these assets, which are also known as the installed base or manufacturing plant. This routine checkup helps ensure everything runs smoothly and efficiently. To prevent failures, a company should implement preventive maintenance. This involves scheduling and systematically performing maintenance tasks at regular intervals set by the maintenance team. These intervals are typically defined in two main ways. Based on information from the machine manufacturer, manufacturers offer technical details on how to operate the machine correctly and the expected lifespan of components. The maintenance team uses this information to schedule part replacements before they reach the end of their expected lifespan, ensuring optimal performance and avoiding unexpected failures. Based on information collected from actual operation, here the maintenance team tracks past failure occurrences to understand how frequently they happen. They then schedule part replacements at intervals shorter than the average time between failures, aiming to prevent issues before they arise. This approach can raise concerns about the efficiency of preventive maintenance, since parts might be replaced even if they're still functioning well. However, in high-stakes sectors like healthcare and aviation, timely replacement of parts is crucial due to the severe consequences of potential failures. Similarly, in industries where environmental damage could occur from a failure, replacing parts before they reach the end of their lifespan is necessary to prevent any possible harm. Even with preventive maintenance, there's still a chance of part failures and machine downtime. This can happen due to potential issues with the replacement parts themselves, contamination during the replacement process, or even human error. Unlike preventive maintenance, predictive maintenance isn't scheduled ahead of time. Instead, it's based on real-time monitoring of the machine's parts and components. By measuring specific variables, predictive maintenance determines the optimal moment for intervention, ensuring that maintenance is performed only when it's truly needed. The most commonly monitored variables in maintenance include vibration, temperature, noise, and electrical power supply. Under normal operation, these variables usually follow a standard pattern. When they deviate from this norm, it can indicate a loss of efficiency or increased wear on parts, signaling potential imminent failure and the need for timely intervention. Monitoring these variables involves using various measurement instruments such as accelerometers, thermographic cameras, mechanical stethoscopes, multimeters, and tachometers. Specific sensors designed for each variable are connected to electronic networks, which transmit data to computers. Technicians then analyze this data to decide when maintenance is needed based on the insights gained. The key feature of predictive maintenance is replacing parts or components only in the final stage of their useful life. This approach helps maximize the component's lifespan, enhances machine availability, and reduces overall costs. To ensure high-quality service, maintenance is managed through analytical techniques and methods such as centralized supervision or sampling. This systematic approach helps to reduce the need for unnecessary preventive maintenance and lowers the chances of corrective maintenance, leading to improved efficiency and cost-effectiveness. Corrective maintenance is defined as maintenance conducted after a failure has occurred, with the goal of restoring an item to a condition where it can perform its required function. A failure in this context is described as a state where an item cannot fulfill its intended function, excluding situations where the inability is due to preventive maintenance, planned actions, or a lack of external resources. In predictive maintenance, various sensors continuously monitor vibrations, temperature, and electrical properties throughout the machine's operation. This real-time monitoring ensures any deviations from normal performance are detected early. Measurement instruments such as vibration meters and analyzers track machine vibrations, thermometers and thermographic cameras measure temperature, and tachometers assess the rotation of shafts and pulleys. Intermittent monitoring, in contrast, is performed at specific intervals, usually by a qualified professional, to periodically check the machine's condition and ensure it remains within acceptable parameters. In preventive maintenance, which is performed with machines stopped and disassembled, various general use equipment and measurement instruments are utilized, including feeler gauges, ultrasonic thickness, gauges, penetrant testing, X-ray inspection, vicecometers, laser alignment tools, wireless aligners. Another commonly used device for measuring vibrations is the accelerometer. Typically, accelerometers consist of a mass, a spring, and piezoelectric crystals. When the machine vibrates, the mass spring system presses against the piezoelectric crystals. This pressure causes the crystals to generate an electrical current proportional to the vibration's acceleration. The current is then transmitted to signal receivers and converted into visual information for analysis. Vibration meters are straightforward instruments designed to measure the vibration of machines and equipment. They often use accelerometers as data collection sensors to gauge and analyze vibration levels, providing insights into the machine's operational condition. For temperature measurement, both thermometers and thermographic cameras are employed. Thermometers. These come in two types. Contact thermometers use a sensor or thermocouple placed directly on the surface to measure temperature. Infrared thermometers utilize an optical system to measure the temperature of a surface from a distance without needing direct contact. Thermographic cameras capture temperature by creating a thermal image or thermogram. They are particularly useful in industries with high temperatures, as they allow for safe, non-contact temperature measurements. In maintenance work, diagnosing parts is crucial for making informed decisions about replacements and potential changes in suppliers. This diagnosis involves using equipment for predictive and preventive maintenance, as well as conducting visual inspections. These methods help identify issues and determine the best course of action to ensure optimal equipment performance. For significant surface wear, visual analysis is key to determining whether a part needs replacement. For example, in rolling bearings, both the internal and external tracks can wear down over time. As the bearing is used, the material of these tracks experiences fatigue, leading to the formation of microcracks. These cracks can become visible to the naked eye as the bearing continues to operate. For structural analysis of parts, non-destructive testing methods are employed to detect issues without damaging the components. These methods include liquid penetrant testing, detects surface cracks that are not visible to the naked eye by applying a liquid that seeps into any cracks and is revealed with a developer. Magnetic particle testing identifies surface and near-surface cracks in ferromagnetic materials by applying magnetic particles and observing their accumulation around defects. Ultrasound testing uses high-frequency sound waves to detect internal imperfections and voids, especially useful for examining welded joints. X-ray testing provides a detailed view of internal structures by passing X-rays through the material, helping to identify internal flaws and inconsistencies. If you have any question, type in the comments section. See you in the next videos. Bye.